in? Like when you
Yeah.
basically, I got like cosine theta, d theta.
Mm-hmm.
Now, can I cancel out the cosine theta in the square root, or can I not do that? Yeah, I know it's kind of
Inside the square root.
yeah. So like I had like a square root cosine theta, and then when I put the d theta in, it was on the right. It was times cosine theta d theta. So can I just like cross out the cosine thetas? Is that allowed? Or I
No.
think it's not.
Was one of them on the bottom, or
No,
no?
they were both like numerator.
Like this?
Yeah.
Okay, then you look at this as being like the same as like x to the half times x. Like this is x to the half times x, so you would add the exponents. So this
Oh,
could
so that's-
become like cosine to the 3/2 theta, because you're adding 1/2 and 1 together.
Because see, I was like, I don't think I can just cross them out. And
Yeah, no.
I also thought maybe I could put the cosine theta like on the left side of it, but no,
Yeah.
that doesn't make any sense either.
That's about all you could do there. And if it was on, like, let's say the cosine, like, let's say this was below it, then you would do subtraction of the exponents,
Okay.
right?
That makes sense.
Here we're adding because they're being multiplied. If one of them was on the bottom, it would be subtraction.
Okay, one final goofy question. So if you have like 3 cosine theta, and you take the, you know, we'll do sine, 3 sine theta, take the derivative. I know the derivative is 3 cosine theta, but why does nothing happen to the 3?
The constant multiple rule from Cal 1 says that if you have a constant attached to the front of a function, that it just kind of comes with you as you take the derivative.
Okay, so that would apply even if you had like 3x squared.
Yeah.
Okay.
Yep. If you do derivative of 3x squared, you can just ignore the 3, take derivative of x squared, which is 2x, but then multiply it times 3, and now you have 6x.
Okay.
So it just, I tell my class it comes for the ride, right? If the constant's in front, you take a derivative, it just comes for the ride. It just comes with you. The only time the derivative constant is something else is if it's by itself. The derivative of 3 by itself would be 0.
Oh, okay, got it.
Yeah.
Makes sense. Because I was doing the homework and I was like, it's like I get the core of what's going on. It's just like if you don't remember all that stuff, then you'll typically get tripped up on something.
Yeah, there's a lot of things that we have to kind of make sure we're, you know. Whoa, that didn't come through too good. Let me rewrite it. All right, we're going to start class with this one.
Is this
Still
still 6-2?
6-2. Last problem out of 6-2. We're going to start 6-3 in just a moment. I wanted you to see this one problem because it's got this one little element of it that is a little tricky.
You know what's funny? Dude, like, my 6-2 lecture is like when I knew my 6-2 homework because I didn't do this long. So I like, homework started here. The lecture's continue back here. Homework will start again over here.
You good? You ready? Okay. So look at this thing and you go, well, I don't see anything that I can do like as far as like a basic U sub, right? Integration by parts. You do see a square root, so that maybe lets you go, okay, maybe trig sub, right? Maybe trig sub. But we would have to have one of those 3 forms, right? We would need to have one of those 3 forms, either a square root of a squared minus x squared, or square root of a squared plus x squared, or square root of x squared minus a squared. We need one of those forms. And the issue is that we have that damn x term in the middle, right?
Can we complete the square?
Yeah, completing square. So we did one just like this last class. The big difference, though, is that I have a negative coefficient in front of x squared, and that's going to change a little bit of the way we handle this, all right? So I'm going to complete the square. So let's just work on that part first. What's the very first thing you need to complete the square?
Well, the x squared, you have to x squared has to by itself, right? No.
Have to have a coefficient of 1, right? So can't have a 1 there. I mean, can't have negative in front. So what should we do? Can't be negative 1. Has to be positive 1.
Can you multiply everything by -1?
Factor out negative 1. Can't multiply because if you do that, you change the problem. You can only factor it out. If you had an equation, you multiply both sides by -1.
So you have
If you had a fraction, you could do top and bottom -1. But if you have just an expression, you can only factor it.
So you have to have that exact form, which is what,
ax squared plus bx plus c. I'm going to pull the -1 out. Yeah, we can rearrange it. I'm going to in a second. That's just me factoring -1 out, right? And I'm going to keep that -1 out here like this. Now I'm going to just rearrange it. Right, just switch the order. So that's all the same, right? Haven't changed the problem. All right, now I'm going to complete the square on what's inside here. So I'm going to take the number in front of the x right there, -4. I take half of it, right? -2, and I square that, and I get 4. And that's going to be the number that I add and subtract. Okay, so I'm going to go -1 here, x squared minus 4x. Now here's my magic number coming in here. I'm adding and subtracting 4. Adding 4, subtract 4. You don't subtract 4, add 4. You add 4, subtract 4. And then I still had there -5. Okay, so that's all me just trying to complete the square. The first 3 terms are guaranteed to be a perfect square trinomial. So that will be -1 parenthesis. Okay, these 3 terms will turn into something squared. What is it?
X minus 2.
X minus 2, right? X minus 2, that quantity squared. But I still have these 2 terms over here now, which go together and become -9. Boom. If you go back and you look at our notes from last class, we did a problem like this, and I think we pulled a 4 out, if I'm not mistaken. A 4 came out. Might have been a 9. I don't remember. No? Whatever. It was a 9? It was a 9. We pulled a 9 out when we were doing the completing of the square, and because that we had a square root, we wound up taking that 9 out of the root as a 3, right? What did we pull out here? -1. We can't take a -1 out of a root because that would be, what's the square root of -1? That's an imaginary number. So we can't deal with that -1 the way we dealt with the 9 prior in the previous problem. Do y'all understand? It's a big deal because we can't make that -1 go away. So what I'm going to do next is I'm going to distribute the -1 back through the parenthesis. So when I do that, that -1 is going to go here in front of this parenthesis, not inside. You can't force it inside because it's being squared. And then that -1 will come over here and change that to a +9. So here's where I am now. That is equal to negative parenthesis x minus 2, that quantity squared, but then +9. And I'm going to just reverse the order of that and write it like this. There we go. Just change the order. Everyone see that? Now I'm going to come back here. Integral, square root. Okay, this is 9 minus x minus 2, that quantity squared dx. It's starting to look a little bit more like what we need, right? It's looking like a little bit more like we need. We've got a square root. We've got, this is a number squared, right? Like a squared minus, and this is kind of like the x squared, but it's not quite x. It's x minus 2. So we could do just like a real quick u sub right now. Just a real quick u substitution. Let's just substitute that out for u and then rewrite the problem, and then it should look like one of our formats. Okay, I'm going to do that right now. And can I erase the completing of the square? Anyone need this? We're good? All right, so now what I'm going to do, quick u sub, u is equal to x minus 2. Of course, the derivative of that is just dx, right? Derivative of x is 1, so that's just dx. So I can just rewrite this. Square root 9 minus u squared du. See, because this is a nice, clean little linear expression, x minus 2, when I do my u sub, everything is real nice. This is just u, and then that just becomes du. It's really, really clean, right? Now look at my formulas. What do I use for this when I have this? Is it sine, secant, cosecant?
I think it's secant.
I'm hearing two. I'm hearing it's secant. I'm hearing sine. Everyone sounds pretty.
Oh, it is sine.
It's sine. It's a sine theta. A sine theta. Right? Because what we have is something that looks like a squared minus x squared, right? A squared minus x squared. So our trig sub, so I'm going to continue now. Our trig sub is going to be not x equals, right? Because our variable here is u. So u equals a, which is 3. That's because the 9 is a squared, right? And then sine theta. And then the derivative of this is 3 cosine theta d theta. And then I'm also going to need the square root part, right? I'm going to need to know what that's going to be replaced with. This right here. Without showing the work, you could do this if you needed to yourself. Replace this u right here with 3 sine theta, plug it in, factor out a 9, Pythagorean identity, blah, 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 square root. This would be that. I put dot, 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 because I've done this several times. So trusting you could do that. And now I rewrite the integral, right? I rewrite the integral. If you're unsure what I just did, that gets replaced with this. And then good things happen. Okay, rewriting this integral, it becomes the integral. All right, this whole square root thing, we just said turned into 3 cosine theta. So that's this. Am I done?
You have to replace du.
Yeah, that's just this, right? We got to replace du, but du is 3 cosine theta d theta. So times 3 cosine theta d theta. Those two 3's can come out as a 9 in front. And cosine squared theta d theta is where we are. And I'm going to do something I don't normally do. I'm going to let you choose. When I came into class, this was my plan, is to do this problem. And at this point, I was going to have this be a quiz problem right now. Everyone take out a sheet of paper, blank paper, start this problem, finish it. So we can take a vote. Do you all want that, or should I not do that and we move on? So how many of you would like to have that as a quiz problem right now?
Can we use notes?
You can use your formula sheets. Okay, so I only have like 2 people. Everyone else wants me to move on. How many of you want me to move on and not give you a quiz like that?
I'll take it.
Oh, really?
I'll just take the democracy.
What is the question again?
Would you like this to be? Would you like that to be a quiz problem right now?
What, like this?
This right here, that integral right there. Would you like to show me you know how to do that as a quiz problem, or do?
Problem we're doing right now, or is that a separate problem?
I'm in the middle of a problem, right? But I have to continue. I want you to finish it. That's what I'm saying. That would be your quiz problem, is for you to do that. Finish this off. I'm not seeing eager.
I mean, I'll push it.
I see a couple people are like, please give this to me. And I'll be honest, this is an easy problem at this point. This should be an easy problem at this point, because this is like last week, right? So we should be like, this is what we're trying to get it to, is something like this, right? So we're not going to do the quiz. I can just. No, you're not disappointing me.
No,
You're not.
On something completely different.
Yeah.
So that 9 seems like magic to me. What's going on with that?
Well, 3 times 3. 9. 9's come out in front.
The coefficient, pull it out.
Right? Constants can just come out.
Okay.
Yeah.
Okay.
Yeah. That's
I
all.
don't know why I thought it was bound to the angle. I guess that's only if it's like 2 theta.
Oh, that's only if that 3 is inside the argument of the trig function. In there with it. In the theta.
You guys can say it.
All right, I'm going to continue, but just side note to yourself, this could have been a quiz, and how would you have done on it? If you would have failed that quiz, then you're not where you need to be in this class right now. You need to be at a different place than you are, right? Because you should be able to look at this at this point. I'm just being honest with you. I'm not trying to be mean. Just being honest. This is cosine squared. You should know what comes next. Power reducing formula, or half angle formula, however you want to look at it. And then that is split in 2 pieces. You're actually going to get a cosine 2 theta in there, and that, when you do the antiderivative, you're going to wind up using a double angle identity. We're about to do it, but you should recognize it now. Like, that should be something you recognize at this point. And what if it was cosine cubed?
You would split it up, right?
You would peel one cosine off, and the cosine squared would be 1 minus sine squared.
Identity stuff.
Yep.
U sub and all
Yeah, exactly. All right, I keep going. So at this point, I replace this cosine theta with 1/2, 1 plus or minus on this, plus cosine 2 theta. That is the identity that I use to get a cosine squared and kind of kill that squared off. Right, there's a give and a take to this formula. You get rid of the squared, but you gain a 2 theta, right? And some other stuff. But this, I can pull the half out front, so 9/2 integral. I still have 1 plus cosine 2 theta in there, d theta. And now I can do the antiderivative of each one of those separately. So this is going to be 9/2. Okay, no more antiderivative because I'm actually doing no more integral sign because I'm doing the antiderivative. Antiderivative of 1 is theta, right? Because our variable is theta, good. And then this one, we've done this hopefully enough that you know that that's 1/2. You have to scale it, sine 2 theta plus c. Right? Antiderivative cosine is sine, so we should expect to see sine 2 theta, but we have to scale by the half to kill off the 2 that would come out with the chain rule.
The 2's the A, right? The 1 over A.
Yeah, exactly. That's the 1 over a. Exactly. And now we need to do our triangle and stuff like that, but the problem is this trig function involves 2 theta, not theta, and our information is, everything that we know about is in reference to theta, not 2 theta. So I'm going to, and this happens every single time you have a cosine squared or sine squared. Every single time you're going to wind up with this right here having to be converted. This will have to be converted to 2 sine theta cosine theta. That's a double angle identity from pre-cal. And then the half and the 2 cancel. Reduce, however you want to say that. 9/2 theta plus sine theta cosine theta. So if I can just figure out what sine theta is and what cosine theta is and what theta is, then I'm in business. So where do I go to get that information? I'm going to need a reference triangle, but the triangle comes from what information?
From X, the original.
The trig sub. The trig sub that we did is where we get the information for the triangle. And the trig sub that we did was u is equal to 3 sine theta, right? That was our trig sub. And from that, I create a ratio on the left side. U over 3 is sine theta. And then from that, I draw my triangle. Here's theta. Sine, by definition, is opposite over hypotenuse. So this is u, this is 3. Right? Opposite hypotenuse. And that forces this side to be the square root of that one squared minus that one squared. So 9 minus u squared. You look like you want to say something. No,
Well,
you're okay.
We also just defined cosine and sine earlier in the equation anyway.
Yeah, what do you mean earlier?
Because we said that
Oh, when we did the
square
actual,
root of 9 minus 2
yes.
squared is-
yeah. I don't mention that just because I want my students to like be completely okay with this, right? But yeah, we did earlier define cosine, so it actually was there, and we defined sine, so we don't even need the reference triangle, right? But again, I think it's worth the effort. All right, moving along. Going to rewrite this now. Oh, we know what sine theta is, right? We know what cosine theta is. Do we know what theta is? No, but how do we get that? Take that, take the inverse sine on both sides. So if I take this, take inverse sine or arc sine on the left, and then take inverse sine on the right. If I take the inverse sine of sine, I get theta. So I'm ready to rewrite this now. I think I'm going to put it right here. 9/2, parenthesis, theta, which is inverse sine or arc sine of u over 3, plus sine theta, which is the opposite over hypotenuse, times cosine theta, which is the adjacent over hypotenuse. All of that plus c. And one more step. One more step.
Yeah, added,
Replace u with,
three, was it three something?
I think it's x minus 2. Was it x minus 2?
Was it three something?
No, that was u. Yes, it was, but we need to get from u back to x now.
Gotcha, okay.
Yeah, you wouldn't want to now replace u with 3 sine theta. You actually go back to where you were. We're trying to get u back to x. So back when we made that substitution, u is x minus 2. Plug it in here, x minus 2, x minus 2, x minus 2 in parentheses squared, and we'd be done. All right. The only reason I did that problem is I want to make sure that you didn't mess up that -1 that we pulled out, that you didn't try and pull it out of the root. You can't do that. Yes?
There'd also be another arc sine if you were over here, right? When the theta, that was only 1/2 the integral, there was the other theta that was floating around out there, wasn't there? So when you have theta plus 9/2, theta plus sine cosine.
Was there another theta?
Yeah, because it was 1 plus cosine 2 theta, and it broke into 2 intervals.
No.
Yeah.
What?
And then we turned that into the theta.
Yeah, this 1 became the theta. That 1 became that theta.
Yes, it did.
Yeah. You put another theta. I think you wrote it and then you wrote it again. Yeah.
Okay.
I should have asked this question earlier, but.
Okay.
Back reset, you said that, when you had that square root, you evaluated, in terms of the 3 cosine theta.
Uh-huh.
Doing all the math that you do in your head.
Yeah.
Instead of doing like the math out, because when you take the derivative before, it kind of starts with 3 cosine theta d theta. And take a shortcut, just forget about the d theta, on that.
Well, will that work for all 3 different trig subs?
I don't think on the tangent.
Yeah, it doesn't. So
I know it's
however you want to do it, you can do it, Like I have them memorized. Like I know what they are, I know when I do a sine theta, I know that square roots can turn to a cosine. I know that because I've done enough, right? And I know what happens for each of the other methods. For you, you're either going to have to derive it or you're going to have to remember it. How you remember it's up to you, right? That's totally your call. But don't remember, it's not, the derivative is cosine theta d theta, right? And then the square root is just cosine theta. There's no d theta. So it's not exactly the same. They look the same, but they're not the same.
Yeah.
But it is a little thing that might help you remember what it is, but it only works for the trig sub a sine theta. It doesn't work for the other ones.
So the only trick to getting the square was you take the middle term, take it by half, square it,
Add, subtract.
add, subtract, got it.
Yep. All right, we're moving on. So we're going to move into 6.3 or 6-3 somewhere. Why does it do that? It's weird. We're going to talk about partial fractions. So on this section, we're going to take 2 complete days for this section. All right? The first day today is going to be us just setting ourselves up to be able to do the problems next class. Because a lot of the problems that we're going to do next class are going to reduce down eventually to one of the things that we're going to see today. All right? And if we can get the problems next class down to these forms, then we should be in business. That makes sense to you? It's like we want to make sure that we have these simpler elements in place so that when we get to the uglier stuff, break it down to become this, we're good. So the first thing that we need to know, preliminary thing, is formula 17 on your sheets. It's a formula for the integral, and I'm going to put something up here for you. So when we were very early in this class, I told you about this formula right here, and that this comes up a lot, and that the antiderivative of that is inverse tangent of x plus c. I said this is something we'll see a lot in this class. You need to kind of burn that in. Do y'all remember that?
Yeah.
Yes?
It's the same thing.
It's basically the same formula, except instead of having a 1, we have an a, right? So this is a number, and this is like the x's, all right? So that's kind of like, that used to be x squared plus 1 squared dx, right? That used to be an x. Now we're saying that if this is something other than 1, then the formula just changes a little bit. You have to do 1 over a here, and then whatever the variable is in here, divide it by a. Okay? That's now, I could prove that formula to you, but I'm not going to, because it would take too much time. But I'll show you how it would be done. If I wanted to prove to you that that formula is true, what I would do is this. I would do the integral, and let me use x instead, so it looks a little bit more familiar to us. If I was going to try and prove that formula to you in terms of x, what I would do is I would use trig sub. I'd use trig sub, but I would rewrite this problem like this: square root of x squared plus a squared, and then all of that, what? Squared dx. I've noticed that that's the same as the root being squared. And then I'd use a trig sub on this. I'd go through all the mess of the trig sub, work everything out, and at the very end of it all, I would get this. Do you believe me that that's what would happen? Okay. Trust that it would happen? That's what you get. So let's not do that. Let's trust that that's what would happen, and let's just do this. Let's just look at a couple of examples of this, okay, to make sure you know how to use a formula. So what if we wanted to do this? Not trying to trick you here. This would just be what? 1/3 inverse tangent. But for us, we're not using u, x over 3 plus c, right? Do y'all see that? Just figure out what the number is that's being squared. In this case, it's 3 squared is 9. And then the variable here we have is x, not u. Questions on that? What about this? What's a?
That's 5.
A is the square root of 5, right? See, if it's 9, we all know the square root of 9 is 3, right? But if I give you 5, what's the square root of 5? I don't know, square root of 5, right? So that's what a is. So I put 1 over the square root of 5, inverse tangent of x over square root of 5 plus c, and I'm done. Yeah? What about this? So you would think u sub here, right? I mean, if you did a little quick u sub, right, then that u would be x minus 2, and du would be just dx, right? So this could be rewritten, and that would eventually turn into u, and then you could use a formula, right? So I recognize right now that what's in here is linear, and that when I take its derivative, I get 1. So I know that even if I do a u sub, nothing's going to change, and I can go directly to the formula. 1 over 4 inverse tangent, but it won't be x, it'll be what? X minus 2 over 4 plus c.
And so that only works when it's linear?
That would only work if it's linear, and that's a 1. I'm about to give you one that's not a 1. Okay? So what if I change the problem and I do this? 16 plus, what if I do 2x plus 1 squared dx? How do you think that changes things?
Factor out of 2.
You're going to have to scale that. You're going to have to scale your answer by a half. You're going to have to kill that 2 off. See, because if I do a u sub right here, u's 2x plus 1, what's du? 2 dx, right? And you don't want that 2. You got to kill it off. So what I would do is this. I would say, this is like the a that we had in the cosine one, where you always had that 1 over a out front. Same sort of principle. I'd have to do 1/2. That would kill that 2 off. Then I could continue with the formula. 1/4 inverse tangent of x, 2x plus 1 over 4 plus c.
Okay, so you can do it completely as normal so long as you like factor that.
As long as you take it, and it only works if this is linear, okay? If this isn't linear, then it won't work. Let me give you one more. I'll try and see if we can generalize it even more. What if I had this 1 over, what if I had some number squared, I don't know what it is, plus, I'll use a squared, and then what if I have in here something that's linear squared, dx. Let me say that this linear expression looks like this, bx plus c. I couldn't use ax plus b because I was already using an a over here.
So you'd have to scale out the b.
So I need what in front here? 1 over b. And then the rest would be inverse tangent. Oh wait, I forgot the, sorry. I forgot the 1 over a. 1 over a, inverse tangent of bx plus c over a plus c. Now that's a different c, that's capital C, this is little c. All right, we should all feel comfortable that if we get to anything like this, we're happy, right? Because we have a formula for it. We're like, yes, all right?
And so like you said, you don't even have to do U sub because
Nope,
it all.
don't do it. Yeah, just go right to the answer. Because we get to a point in these problems where how long is this problem going to take if we have to do every little detail, right? Like let's say we didn't have this formula, right? And we had to do trig sub on this. Like if that's just part of a bigger problem, it'll take us 3 hours to get through a problem, right? So we do need to be able to fall back on some formulas. All right, let's look at this one. All right, that was the first preliminary. Now, here are some integrals we should be able to handle right now. Right, so now we're just going to kind of look at some integrals that all have kind of a certain characteristic, and we're going to convince ourselves that if we ever see this again, we're going to be like, you know, party time, right? We're like, yes, this is good, this is good. All right, notice the form of this integral, 2 divided by x minus 4. What I have is an integral where the numerator is linear, right? I mean, sorry, the numerator is a constant, right? 2 is a constant. And the denominator is a linear expression in x. I don't want you to memorize what happens right now. I want you to think about what happens. If I make a u substitution of the bottom, right? Then the derivative of that would just be 1. And so I'm not going to have to scale anything, am I? And that integral would really then turn out to look like a 2 over u du, wouldn't it? If I had made that substitution. And that's the same as pull the 2 out, 1 over u du. And the antiderivative of 1 over u is natural log of the absolute value of u, right?